So welcome everybody to this new IM seminar. We are more than delighted to have with us Philipp Scholl. Philipp Scholl obtained his bachelor and master degrees in mathematics from the Technical University of Munich in 2021, and is pursuing his doctoral studies in mathematics under the guidance of Professor Cnr-Iac that we have had already as a host in our seminars at the Ludwig-Maximilians-University of Munich. His research revolves around physical law learning, a field that aims to automate the inference of physical laws from experimental data. It's with extreme pleasure that I leave the floor to Philip. Please, Philip.
Okay, thank you, Flavio, for the nice introduction. So, today I will be talking about the well-definedness of physical law learning, specifically the uniqueness problem. This work has been done together in a collaboration with Aras Basho and Gitta Coutinho from the Ludwig-Maximilians-University of Munich and Holger Boche from the Technical University of Munich. So in case of questions, I'm happy to answer understanding questions right away, such as you can follow. For more deeper questions, I think it helps if we answer them at the end. Okay, so what is physical law learning? For the most time of human history, scientists had to come up with physical laws on their own by observing physical experiments. However, due to the success of artificial intelligence in almost every area, physicists and engineers decided to try to automate this process, which means they're aiming for artificial intelligence, best captured, I think, in these paper titles, AI Descartes, AI Feynman, AI Physicist, where they try to automate the process of deducing and inferring physical laws upon receiving data from a physical experiment. The problem we are interested in today is the PDE learning problem. Here we assume that the physical law can be captured by a PDE, and so the input to our artificial intelligence will be data about some solution U of some PDE given by F. And the output or desired output of the AI should then be the function F, which describes the PDE solved by U. So far, most of the literature is interested in algorithms, how to achieve this goal. We, on the other hand, want to start defining the PDE learning problem from a more theoretical point of view. So we want to define an operator O, which takes a function U as input and outputs a function F, and we want to investigate this operator. We want to ask questions about its robustness, for example, but also, first of all, we want to ask questions about its well-definedness. And this is what this talk is about. So the well-definedness involves two parts. One part is for each U, the existence of an F, and the second part is of each U, the uniqueness of F. And here we specifically will be talking about the uniqueness of F today. So to motivate this further, let's look at the following example where we actually don't have the uniqueness. So on the left-hand side, you see the one-way wave equation, and on the right-hand side, the coordinate de Vries equation. Two different PDEs modeling different physical phenomena. However, for some initial values, they're solved by the same function U. And this actually has been observed in previous papers in this field, or at least by one, in an experiment where they simulated data from the KdV equation, and the goal was to learn the KdV equation using their algorithm. The problem, however, was that the algorithm outputted the one-way wave equation instead. But because the authors knew that this is not the correct equation, that's not the equation they wanted to learn, they actually decided on just changing the initial values until they got their KdV equation, which is a very so for this case, they solved the problem. However, this is a very artificial way of solving the problem because physical law learning is all about you don't know yet what the correct PDE is. So in practice, that's a method you couldn't use, and you would just assume that the one-way wave equation was the correct one, and you would use this then for new experiments and would expect the one-way wave equation to give you good predictions. And So this is apart from our theoretical considerations before, this is the practical reason why I think this is a very interesting topic. And yeah, so we want first develop a theoretical understanding of the question, when is there only one PDE solved by a function u, and when are there multiple ones? And then we want to use this to deduce algorithms to numerically check when the PDE is the unique explaining one. And yeah, before we go to these two questions, I want to discuss the uniqueness problem in more detail and define it exactly. So what do we mean? So first of all, you can never ask, okay, is there any function, any PDE involving just any derivative of u, like the thousandth derivative or whatever. So you should, before that, you should select derivatives u alpha 1 to u alpha L for which you're interested in the uniqueness. So alpha 1 to alpha L are some multi-indices, and you fix some natural number n. And then we ask the question if there's a unique function f in some set of functions v, such that the nth time derivative um, of u equals f of u alpha 1 to u alpha L. So we are interested in the uniqueness of f in this setting. However, we might want to be a bit more broad, so we could also allow f to depend on t and x directly, or we would allow f to also depend on the time derivative of u, so we also include ODEs in our whole framework. And yeah, to put all of these cases together, we use the following definition from now on. And yeah, so with G1 to GK, we denote either a projection on one of the coordinates, so t or x, or any derivative of u that exists, or simply the function u. So all of the functions we used inside of f before. And yeah, we fix some natural number n and ask if there's a unique function f in some set of functions v, such that the nth time derivative of u equals f of g, where g is simply the vector of g1 to gk. And yeah, so this property is quite complicated to analyze, and that's why we want to go to a different property, which we call trivially annihilated. So let now g be just any function mapping to Rk, and yeah, let v be some set of functions which include the zero function. We then say that g is non-trivially annihilated in v if there exists some function, some non-zero function in v, such that h of g equals 0. And otherwise, we say that g is only trivially annihilated in v. So yeah, just to get a feeling for this property, I prepared two examples. So the first example is, consider the function g of x equals minus x squared. And for as a function set, we consider v equals 0 and the real u function. Then we actually get that g is non-trivially annihilated in v, since the real u function maps g to 0. However, if we consider g again as minus x squared, but this time v as the set of linear functions, then we get that g is only trivially annihilated in v, since minus x squared equals 0 for all x in R, if and only if a equals 0. So, and yeah, now why are we interested in this property? And this is because of this proposition. What does this proposition give us? So let v be now any set of functions which is closed under addition and subtraction, such that there exists a function f in v with f of g equals the nth time derivative of u. And then we actually have the following. Then f is the unique function in v with, such that the PDE holds if and only if g is only trivially annihilated in v. So this proposition is actually quite powerful, as it translates the uniqueness questions from before into a question about sets of functions v. And it is actually the basis of everything we will do in this talk, since the non-trivially annihilated or only trivially annihilated property of some function sets have actually already been studied in different fields under different names, and we will look at this later. But for now, because it's so important, And because the proof is so easy, I will continue on showing it to you. So let f and g in V be functions such that f of g equals the nth time derivative of u, and g of g also equals the nth time derivative of u. Then if we do a simple transformation, we get that f minus g of small g equals 0. And now if we know that small g is only trivially annihilated in V, we directly get that f equals g. However, if we know that g is non-trivially annihilated, then we get that there's exists actually a function big G which is different than f, and for which still this equation holds. So yeah, this translates now our complicated property to a maybe simpler one, and we will consider next the case of linear PDEs, because here this property is the most familiar one probably. So here we get namely that the function g1 to gk are linearly independent over R if and only if they are only trivially annihilated in a set of linear functions. And yeah, because of this observation, we get the corollary basically for free. So if we assume now that there exists at least one linear function such that f of g equals the nth time derivative of u, then there exists a unique linear function f such that this holds if and only if g1 to gk are linearly independent. So yeah, let's see how this works on some examples. Yeah, let's consider the function u of tx equals exponential of x minus at for this, which solves the linear PDE ut equals minus au. And now the question might be, is this the unique linear PDE of the form? Now we will be looking at different forms. So first of all, in this form, ut equals f of u ux. And yeah, so we just have to check if u and ux are linearly independent, and actually they're not, since ux is actually u, so u and ux are not linearly independent, and therefore we get that there exists another PDE in this form, which you can see here, ut equals minus aux. Next question would be, okay, in this form, so ut equals f of t x u, and actually again we have to check the linear dependence of t, x, and u, and since all of them are linearly independent, we get that this is the unique PDE in this form. And yeah, so how now we discuss the theory of linear PDEs, and the question is, how do we use this now numerically? So what we have to do, as before, we have to check if g1 to gk are linearly independent, but this time we want to do it numerically. So we're just given data points, some evaluations of g1 to gk. So what you usually would do, you simply check the rank of the matrix defined by the evaluations of these k functions. And yeah, this can be done by checking the least singular value of a matrix. And yeah, problem here is that numerical derivatives are very unstable, and thus linear independence will be lost. And for this reason, we decided to use the following algorithm, the stable feature rank computation, or also S-Franco. So first of all, we compute G1 to GK using varying orders of finite differences. So finite differences is a numerical algorithm to compute the derivative if you just have access to data. And varying order usually gives you different levels of approximation. Then in the second step, we calculate the least singular value for all the orders and assess if the least singular value decreases exponentially for increasing order, since this is exactly what you would expect if your least singular value is 0, meaning that g1 to gk linearly dependent. And yeah, so let's see how this works in practice. We reconsider our old example. So u of tx equals the exponential of x minus at. We chose a as 3 for our experiments. We know this solves ut equals minus au. And we ask the same question as before. So does u solve a unique linear PDE of the form ut equals f of u ux? And we already know that the answer is no, because u and ux are linearly dependent, but now we want to see it numerically, and this is exactly what we can see here. So on the x-axis, you see the finite differences order, and on the y-axis the smallest singular value. And as you can see, we have a exponential decrease of the smallest singular value, which indicates that u and ux are actually linearly dependent, and so we don't have uniqueness. Okay, so this was the first part for linear PDEs, where it was all pretty simple because the uniqueness is equivalent to linear independence, which is even numerically accessible. And yeah, but now let's go to a bit more general PDEs, to polynomial PDEs. So here there's actually a property which is very similar to linear independence, and that is algebraic independence. Let's discuss this first. So we call functions f1 to fq algebraically dependent over a field K if there exists a polynomial P with a non-zero polynomial P with coefficients in K, such that P maps f1 to fq to 0. And if no such P exists, we call f1 to fq algebraically independent. And yeah, since you can see how similar this property is to linear independence, just instead of a linear function, we use a polynomial P here. We get also the same statement again, basically. So the functions g1 to gk are algebraically independent over R if and only if they are only trivially annihilated in the set of polynomial functions. And yeah, now this directly as before gives us the following corollary. So assume that there exists at least one polynomial function f with f of g equals the nth time derivative of u. Then there exists a unique polynomial function f such that this holds if and only if g1 to gk are algebraically independent. And yeah, let's see this on one example. So let here u of tx equal 1 over t plus x, which solves the PDE ut equals ux. And again, we ask the question if this is the unique polynomial PDE of the form ut equals f of u ux. And yeah, so what we have to do, we have to decide if u and ux are algebraically independent, and actually they are not, since u squared plus ux equals 0. And so yeah, another PDE solved by u might be ut equals minus u squared. Then the second question, ut equals f of t ux in this form. So are t and ux algebraically independent? And yes, they are. So we have uniqueness. And the last question, ut equals f of tx ux. And actually, here we have that tx and ux are linear algebraically dependent, and because of that, we don't have the uniqueness. So however, the problem with algebraic independence is that it is numerically not that easy to verify. And because of that, we will do some more work for this field. So let's introduce algebraic functions. We call a function f an algebraic function if there exists an irreducible non-zero polynomial p with p of x, f of x equals 0 for all x in u. So basically, an algebraic function is a function which is a solution of a polynomial equation. Some examples for algebraic functions would be polynomials, rationals, x with fractional powers, but also functions you can't describe with elementary operations, like the function which fulfills f of x to the power 5 plus f of x plus x equals 0, and many more. However, there are also many functions which are not algebraic functions, like the sine, cosine, exponential function, and so on. And yeah, so one interesting fact actually about algebraic functions, which is maybe quite surprising because algebraic functions are a way bigger set than polynomial functions, is that a function g is non-trivially annihilated in the set of polynomial functions if and only if it is non-trivially annihilated in the set of algebraic functions. This means that all the statements we derive here for polynomial PDEs are actually also valid for algebraic PDEs. And another fact about algebraic functions is that if you use an algebraic function and alpha a multi-index such that u alpha exists and is continuous, then u alpha is also an algebraic function. And this gives us the following interesting thing. So if u is algebraic, then also g1 to gk are algebraic. And this is interesting because for the next theorem, we will restrict ourselves to algebraic G1 to GK, but we know that this only means that we restrict ourselves to algebraic U. And yeah, so this is the theorem. So let G1 to GK be K algebraic functions and assume that there is a polynomial f such that f of g equals the nth time derivative of u. So if k, the number of functions g, is greater than m plus 1, the number of variables, then we immediately have that f is not the unique polynomial with f of g equals the nth time derivative of u. And yeah, if now k is less or equal than m plus 1, then we get that f is not is the unique polynomial with such that the PDE holds if and only if there exists one point tx in U such that the rank of the Jacobian is k. And yeah, so this now translates our algebraic dependence from before to some more testable arguments, since the first one is simply a counting argument if k is bigger than m plus 1, and the second one is a question about the Jacobian rank, which again can be done by computing least singular values, but we will see this later. But for now, let's see how this would work out for the example from before. So we again use u of tx equals 1 over t plus x. And yeah, so the question is this the unique polynomial PDE of the form ut equals f of u ux? We already know all these answers, but now we're gonna see how to use this theorem to deduce these answers. And yeah, here we again get no, since we have to compute the rank of the Jacobian, and by looking at the Jacobian and knowing that because of the symmetry, we get that ut equals ux and utx equals uxx. We have that the Jacobian is always singular, and because of that, we have the uniqueness. And also one thing to mention, maybe because we're using u and ux, so we have two functions, and we have um, that m equals 1, so we have k is less or equal than m plus 1. We are in the second case, and that's the statement that we use. And here again, we have that 2 is less or equal than m plus 1. And yeah, we again have to check the Jacobian here because of this. And the Jacobian is the following. And you can easily see that the Jacobian is not everywhere singular. And because of that, we get that that this is actually the unique polynomial describing a PDE solved by u. And now for the last question, as before, we have now three functions, tx and ux. So we have k equals 3, which is greater than m plus 1. And because of that, we're in the first case from the theorem, and we immediately get that this is not the unique polynomial there. And yeah, so we saw how this theorem works. And now, as I already told you, I want to use this to deduce the algorithm. So here we use the Jacobi rank computation. Again, we have the numerical problems with the derivative, and that's why we use the algorithm like this. So first of all, we compute G1 to GK using finite differences. Then we compute the Jacobian of G1 to GK at specific points using finite differences, and calculate for all Jacobians computed before the least singular value. And yeah, we repeat the steps 1, 2, 3, this time for a different finite difference order. So the idea is that in the first step, we do it with a very low finite differences order, and the second step with a very high one. And then we assess if there's at least one point without a strong decrease in its smallest singular value. And yeah, so let's see how this algorithm works then exactly. So we reconsider the same example as before, u of tx equals 1 over t plus x, solving the PDE ut equals ux. And then the question is, does u solve a unique polynomial PDE of the form ut equals f of u ux? We already know that this is not a unique one, but now we want to do it numerically. And yeah, for this we use the JRC I just introduced. So in the upper plot, you see the least singular value of the Jacobian at different places when the Jacobian and Ux were computed using finite differences with order 2. And yeah, you see that it's around 10 to the power of -5, so quite small already. But in the second plot, you see it for the high finite differences orders, and you see that the least singular value goes down everywhere to 10 to the power of -13. So we see a decrease at every point. And so we can deduce that the Jacobian was actually singular at every point in space. And because of that, we get the non-uniqueness as we had it before. And yeah, let's go to the last class of PDEs, analytic PDEs. So for this, let's first introduce analytic functions. A function f in C infinity is called an analytic function if at each point x in X there exists an open set, an open neighborhood around X in its domain such that the Taylor series of f converges pointwise to f on V. And we denote the set of analytic functions on X as C omega. And yeah, some examples for analytic functions are polynomials, rational functions, exponential functions, sine. Some non-analytic functions are any function that is not C infinity, but also there are some functions in C infinity which are not in C omega, like the standard example. And yeah, now let's start with stating a fact proven by Mitiagin from 2015. So let f be an analytic function and d is set in its domain such that it has a positive k-dimensional Lebesgue measure. Then we actually have that if f is 0 on the whole set D, then also f is 0 on its whole domain. And why is this interesting? Because it's very, you can see maybe the relation already to being non-trivially annihilated. And yeah, so you get quite easily the measure criterion for analytic functions, which goes the following way. Assume that there exists at least one analytic function f, such that f of g equals the nth time derivative of u, and set d now as the image of g. Then if the k-dimensional Lebesgue measure of D is positive, then f is the unique analytic function such that U solves the PDE described by f. And yeah, as before, let's look at an example here. So we define U of tx as x plus bt times exponential of at, where a, b are positive reals. And yeah, we know that this solves the PDE ut equals au plus bux. And the question now would be, is this the unique analytic PDE of the form first ut equals f of u ux? And yeah, so what we have to do, we have to check if the Lebesgue measure of u ux, the two-dimensional Lebesgue measure of u ux is positive. And so let's look at the image of those, and the image is r times the positive reals, and thus the Lebesgue measure of the image is actually infinity, but most importantly, it's bigger than 0. And we know that, so this gives us uniqueness. If we now ask, for example, for this PDE, we get that it is not the unique PDE there, since the image has a Lebesgue measure of 0, because we now have to consider the three-dimensional Lebesgue measure for this case. And yeah, so we found a nice property which gives us the uniqueness. However, it's just a sufficient condition. The question would be if also it's a necessary one, and actually this can be disproven, but it's a bit more complicated. And yeah, another problem with this theorem or corollary is that it's not so easy to verify the Lebesgue measure, the size of the Lebesgue measure of a set numerically. And because of that, we introduced the next theorem, which is the Jacobi criterion for analytic functions. So assume that there exists at least one analytic function such that f of g equals the nth time derivative of u, and assume that g1 to gk are continuously differentiable. And yeah, now if there exists one point tx in U such that the Jacobian of G has full rank, then f is the unique analytic function with f of g equals the nth time derivative of u. And yeah, so this statement I think is very interesting for many different reasons. So first of all, it's very similar to the Jacobi criterion for PDEs before. However, there are some extensions. So first of all, we're not as restricted before anymore. So we're not looking at algebraic functions G1 to GK anymore. Instead, we're looking at continuously differentiable functions. Then second, it gives us the uniqueness not only for polynomial PDEs, but also for analytic PDEs, which is a strictly a greater class. However, while being more general, it also has a flaw, which is that it is only a sufficient condition and not a necessary one. And yeah, because of this, we can only use it for one direction. But yeah, also very interesting is that the first proof for the Jacobi criterion for polynomial PDEs actually works completely algebraically, while the proof for this theorem works completely analytically. And it's actually quite simple. That's why I'm gonna show it to you now. So just some proof sketch, the most important ideas. So first of all, if we have that the rank of the Jacobian is full at one place, we can use the inverse function theorem, and which gives us the existence of an open set V in the image of G. And yeah, since the open set always has a positive Lebesgue measure, we also know that the image of G has a positive Lebesgue measure. And now the measure criterion only directly gives us that G is only trivially annihilated in C omega, and therefore we get the uniqueness. And yeah, so this finishes basically the proof already. And yeah, also as before, for the polynomial PDEs, we can easily verify the Jacobi criterion, and that's why we're already finished with analytic PDEs and can now use it in some experiment. Here I try to use a bit more complicated function for now, because we're not gonna compute it ourselves, we're just gonna use our algorithm to do it. So we look at this function, which solves the following bit more complicated PDE, analytic PDE, and we want to ask now if this is the unique analytic PDE of the form ut equals f of u. Again, use the JRC algorithm, the Jacobi rank computation, and we do exactly before now what we did before, and you can see that the finite differences don't, or at least singular values doesn't depend strongly on this the order of the finite differences. You can see there's no decrease in there. And because of that, we can safely say that this is the unique analytic PDE solved by U. And yeah, so to summarize, we identified the uniqueness of the PDE as a key issue of physical law learning and generated a theoretical understanding of the uniqueness problem for different classes of PDEs. Afterwards, we used this theoretical understanding to deduce numerical algorithms to identify cases in which the problems occur and verified them experimentally. So thank you for your attention. And yeah, so these are the papers the talk is based on. These are my references. And yeah, I'm happy to answer now your questions.
So thanks, Philip. There's a couple of questions from YouTube chat that I will show. First one. Is the space V in the trivial annihilating proposition more general than a vector space?
Let me just quickly go back there. I guess. Can I go quicker? So I think this one. And I mean, it is not way more. So for a vector space, you have, of course, addition and subtraction, but you also always have that you have a scalar multiplication in there. You don't need this necessarily here, but all the classes we're looking at will have them. So it is a bit more general. You could do it for very special classes of functions if you want to, but yeah, in general, a vector space verifies it for it.
Another question by Nicole also. So the rank of the Jacobian controls algebraic independence?
Yes, if you consider algebraic functions. And that was the problem why we had to restrict that theory, unfortunately, to algebraic functions. And yeah, but there's a known fact from algebraic theory, I think mostly algebraic geometry actually, where it's from, that the Jacobian controls the algebraic independence.
Okay, and then apart from linear, polynomial, and analytic PDEs, which I mean, do you foresee any other? You're actually working on analytic PDEs more than else, right?
Yeah, mostly. I also consider I wanted to go as broad as possible because I just wanted to see where the limit is. And for this, I can actually show something. Now I have to just guess which slide it is. Did it jump? Okay, bit more. Yeah, this one. So I actually also considered what if the right-hand side of the PDE is actually just a continuous or a smooth function. And here we get actually the following. So if D again is the image of G, then the function G is only trivially annihilated in CP for any P between 0 and infinity, if and only if the closure of D is equal to R to the power of K. So in this case, if you want to go broader than analytic functions, you basically lose uniqueness unless you have almost a surjective function G, which from what I've seen is very unlikely. Plus, it's also numerically, I don't know how one might verify that a function is numerically verify that a function is surjective.
And what about numerical issues that you encountered apart from those ones you showed us in applying the theorem to actual cases? I mean, is there
Mm,
any other caveat that you found out during the experimental phase?
It's mostly the problem that I already introduced or like mentioned. It's that the numerical derivatives are extremely unstable, and yeah, as soon as you add in noise, you might lose a lot, and especially because also linear independence is a property which is easily lost due to noise. Both of them together, because all we do is we use numerical derivatives to compute the functions, and then we check linear independence of these. So this is a very highly fragile um, setting already. That's why one has to be very carefully with this. And actually, yeah, I want to make it more robust in the future. So this is still an open topic, but for now it was already like if you see or if you have seen it for linear PDEs, where we had the perfect linear dependence in the sense of that u was equal to u of x, we actually had that the least singular value was around 10 if you use the finite differences order of 2. And so just using these numerical derivatives without any proper considerations in there would yield you the wrong statements from deductions. However, also my setting is not perfectly robust for more noise. So this is still something I want to work on. And some ideas there might be, for example, that instead of checking the linear independence of derivatives, you could use also the integrals of them. But yeah, makes it a bit more complicated.
Okay, I mean the robustness is useful in nasty scenarios
Yes.
that might benefit from the interesting results that you showed us. Okay, if there is no other question, I would like to thank the speaker again for this very interesting and focused seminar. And I just tell the audience that the next IM seminar will be on Wednesday, June the 7th, same hour, and we will show Salvatore Cuomo will provide us another interesting seminar on the topics. Thanks again, Philip, and see you on June the 7th. Thanks, everybody.
Thank you.